Something is happening to the planet you are standing on, and scientists cannot fully explain it. Days are getting shorter, not by much, fractions of milliseconds, but enough that atomic clocks are catching it. The planet is spinning faster than it should be, and nobody has a clean answer for why. The magnetic field that shields every living thing from solar radiation is weakening in ways that exceed what the models predicted. Deep beneath your feet, the solid iron core of the Earth reversed its spin direction. Then its shape began to change. The poles are drifting. The oceans recorded temperatures in 2023 that no instrument in the history of ocean measurement had ever seen before. Each of these things, taken alone, might be a footnote. Taken together, they form a picture that has laboratories working overtime and researchers asking questions they didn't expect to be asking yet. Something massive is unfolding, and no one knows what it means. This is not speculation. These are measurements. Atomic clocks, satellites, seismometers, ocean buoys, instruments precise enough to detect a change in the length of a day down to fractions of a millisecond. They are all reading the same signal. The planet is not behaving the way the textbooks said it would. Some of these changes have leading hypotheses. Some are barely understood. A few remain almost entirely without explanation. What's strange is how many of them are happening at the same time. Were these systems always this dynamic and we simply couldn't see it? Or is something changing? That is the question. And the honest answer right now is that science does not yet know. Pay attention to what comes next. We begin. In June of 2022, Earth set a record that nobody was rooting for. The planet completed a full rotation in less time than it ever had since precise measurement began. Not by much. The difference was 1.59 milliseconds. That is a number so small it seems like noise, like a rounding error, like something you would throw out of a data set. It was not noise, it was a signal, and scientists had been watching it build for years before that record fell. To understand why this matters, you have to understand how we measure a day. The obvious answer is the sun. Watch it rise, watch it set, call that 24 hours. That method worked for most of human history. It stopped being good enough once timekeeping became the backbone of everything from satellite navigation to global financial transactions. In the mid-20th century, a different standard took over. Atomic clocks measure time by counting the oscillations of cesium atoms, which vibrate at exactly 9,192,631,770 cycles per second. That number does not drift. It does not respond to temperature or gravity or the mood of the universe. It is, for practical purposes, perfect. What atomic clocks revealed when scientists set them running alongside the planet was something unexpected. Earth is not perfect. Earth wobbles, slows, surges, and hesitates in ways that celestial mechanics alone cannot fully predict. And in recent years, it has been running fast. For centuries, the accepted understanding was simple. Earth's rotation is gradually slowing down. The moon is responsible. As the moon pulls on Earth's oceans, tidal friction acts like a brake on the planet's spin. This effect is real and measurable. Days were shorter hundreds of millions of years ago. Coral fossils from the Devonian period record daily growth rings that show a year containing more than 400 days. The planet has been winding down for a very long time, and the moon has been the reason. So when atomic clocks started showing days getting shorter rather than longer, that raised a question nobody had a clean answer for. What was pushing back? The trend became undeniable through the 2010s. Scientists tracking the difference between atomic time and astronomical time, the actual position of Earth against what the equations predicted, noticed the gap closing in the wrong direction. Days in 2020 were the shortest ever recorded up to that point. Then 2021 broke more records. Then June 2022 broke all of them. The planet was spinning faster than at any point in the modern measurement era, which stretches back to the 1960s. That era is not long in geological terms, but it is long enough that a consistent trend in the wrong direction cannot be dismissed. The practical consequences landed quickly on the people responsible for keeping clocks synchronized with the planet. The system that bridges atomic time and astronomical time is called Coordinated Universal Time, and it is maintained by periodically adding or subtracting a leap second, a single second inserted into the global timescale to keep atomic clocks aligned with Earth's actual rotation. Since the system was introduced in 1972, every adjustment has been an addition. Earth was always running slow relative to the atomic standard, so scientists added seconds to compensate. The prospect of Earth running fast enough to require a negative leap second, subtracting a second from global time, had never arisen before. By 2022, it was being seriously discussed. GPS satellites, internet servers, financial systems, and telecommunications networks are all synchronized to Coordinated Universal Time. A subtracted second would be genuinely unprecedented for global infrastructure. Some systems were designed to handle leap second additions but had never been tested against a deletion. Why is the planet speeding up? Several factors have been proposed, and none fully accounts for the observed acceleration on its own. Changes in atmospheric pressure patterns can push or pull on the planet's rotation slightly. The redistribution of water from melting ice sheets into the oceans shifts Earth's mass, changing its moment of inertia and therefore its spin rate, the same way a figure skater speeds up by pulling her arms inward. These effects are real, they are measurable. They are also not large enough to explain the full magnitude of the acceleration scientists recorded between 2016 and 2022. That gap pointed researchers toward the interior. Something beneath the crust, beneath the mantle, inside the planet's deep structure, appeared to be contributing, and the leading candidate was the inner core. The inner core is a solid ball sitting at the center of Earth, surrounded by thousands of miles of liquid iron in the outer core. Changes in how the inner core moves relative to the rest of the planet can transfer angular momentum between the core and the mantle and crust above it. If the inner core shifts its rotation in a way that gives the outer layers a push, the planet's surface speeds up. It is an exchange of spin between the deep interior and everything above it, and it happens invisibly, far beneath any instrument that has ever been physically placed in the ground. The inner core cannot be reached by drilling. The deepest borehole ever completed, drilled in the Soviet Union over 20 years, reached about 12 kilometers into the crust. The inner core begins at a depth of roughly 5,000 kilometers. Everything scientists know about it has been inferred from the behavior of seismic waves, the faint signals of earthquakes traveling through the planet's interior and emerging on the other side altered by what they pass through. Those signals, carefully read, suggested that something in the core's behavior had changed. And to understand why the planet is speeding up, you have to go to the one place on Earth that no instrument has ever directly reached. The inner core of Earth is a solid ball of iron and nickel sitting at the center of the planet, roughly the size of the Moon, surrounded on all sides by a liquid outer core, thousands of miles deep. It sits under pressure that defies easy description. At those depths, iron behaves in ways it does not behave anywhere else. It is solid, not because it is cool enough to freeze, but because the pressure is so extreme that it has no choice. This is the structure that geologists spent decades treating as essentially fixed, the most stable thing on Earth, almost by definition. That assumption did not survive the data. To understand what scientists found, you have to understand how anyone studies something buried 3,200 miles beneath your feet. No drill has ever come close. No instrument has ever reached the inner core directly. The only tool available is one that nature provides without asking: earthquakes. When a major earthquake releases energy, it sends seismic waves radiating outward through the planet in every direction. Some of those waves travel through the interior, passing through the mantle, through the liquid outer core, and straight through the inner core itself before emerging on the other side of the world at a seismometer thousands of miles from where the quake began. The time it takes those waves to arrive and the way their character changes as they travel tells scientists something about what they passed through. It is a form of imaging, indirect, imprecise by some standards, but the only option available for a place no human will ever visit. For decades, researchers compared seismic wave arrival times from earthquakes recorded at stations around the world. They noticed something. Waves that passed through the inner core along certain paths arrived slightly faster than waves along other paths. This was not random. It suggested that the inner core had an orientation, a preferred direction, the way a crystal has a preferred direction. And over time, as earthquake data accumulated across years and decades, the patterns shifted. The travel times along specific paths were changing. The only explanation that fit was that the inner core was rotating, slowly, relative to the mantle above it. That was strange enough. Then the picture got stranger. A study published in early 2023 analyzed seismic wave data stretching back across more than 6 decades of earthquake records. What they found upended the previous model. The inner core had not simply been spinning faster than the planet around it. Around 2009 or 2010, something had changed. The core had slowed, and by the time the data was fully analyzed, it appeared to have reversed. The direction of rotation relative to the mantle had flipped. It was now turning the other way. The scientific community did not agree on this immediately or uniformly. Others found supporting evidence in separate datasets. The debate is not entirely resolved. But the reversal hypothesis has become the leading explanation for what the wave data shows, and no clean alternative has replaced it. This is the kind of finding that sounds like it should have obvious consequences. If the inner core is spinning in the wrong direction, surely something catastrophic follows. The answer, as best as scientists can say, is that the effects are subtle. The core's rotation affects how energy and material are exchanged between the inner core and the liquid outer core above it. It influences the generation of the magnetic field. The specific consequences of a reversal in rotational direction are not fully characterized, partly because nothing in the observational record had prepared researchers to look for them. But here is what makes it difficult to dismiss. The inner core is not a small component of the planetary system. It is the engine room. Changes in how it moves affect the fluid dynamics of the outer core, which generates the magnetic field that shields the planet from solar radiation. You cannot quietly reverse the spin of a structure that size without it meaning something. Then came 2025. A team of researchers reported something that surprised even the scientists who had been tracking the spin reversal. The shape of the inner core was changing. The outermost layer of the inner core, the region where the solid ball meets the surrounding liquid iron, was showing deformations. Bulges and depressions were appearing where the boundary should be smooth. The inner core was not a perfect sphere. It was changing geometry. To appreciate how strange this is, consider the pressures involved. At the center of the Earth, pressures reach roughly 360 gigapascals. That is about 3.6 million times the atmospheric pressure at sea level. Under conditions like that, the expectation was that the inner core would hold its shape with something close to absolute rigidity. The discovery that it is deforming, that its outer layer is developing an uneven surface, suggests that forces are acting on it that the standard models of core dynamics did not fully account for. Whether those forces are connected to the rotation reversal, or whether they represent a separate phenomenon, remains an open question. And then there is the gold. In 2024, a study based on analysis of volcanic rock formations in Hawaii found geochemical signatures suggesting that material from the core had been leaking upward toward the surface. Specifically, the isotopic ratios of certain elements in those rocks pointed to an origin at depths consistent with the core mantle boundary, or possibly deeper. Among the elements implied was gold. The core contains significant concentrations of precious metals, including gold and platinum, which sank to the center of the planet during Earth's early molten phase when heavier elements settled inward. The idea that any of that material could travel from the core to the surface sounds impossible at first. The mantle is thousands of miles of solid or semi-solid rock. But mantle plumes, columns of unusually hot material that rise slowly from the base of the mantle toward the surface and feed volcanic hotspots like Hawaii, appear to be sampling material from extraordinary depths. If those plumes are pulling trace amounts of core material upward over millions of years, then the boundary between the core and the rest of the planet is not as sealed as assumed. It is permeable, slowly, incompletely, but measurably permeable. None of this resolves into a tidy conclusion. The rotation reversal is confirmed by one major data set and disputed by others. The shape deformation is newly reported and barely studied. The gold leakage is a geochemical inference, not a direct observation, and the physical mechanism that drives it is only partially understood. What connects all of it is the same thing. The inner core is behaving in ways that don't match the model that textbooks built for it. A structure that was supposed to be among the most stable things on the planet has been bending, spinning in the wrong direction, and leaking gold toward the surface, and scientists are still working out what any of it means. Earth's magnetic field is the reason the planet has an atmosphere at all. Without it, solar wind, the constant stream of charged particles pouring outward from the sun, would have stripped away the gases surrounding Earth billions of years ago. Mars lost its magnetic field early in its history. Look at Mars now, a thin wisp of carbon dioxide, a surface scoured by radiation, no liquid water, no life that we have found. The field is not decorative, it is structural. It is the reason anything alive exists on this planet. The field is generated deep inside the Earth, in the liquid outer core. This is the layer that surrounds the solid inner core, thousands of miles of molten iron and nickel in constant churning motion. As that liquid metal moves, driven by heat escaping from the core and by the planet's rotation, it generates electric currents. Those currents produce a magnetic field. The process is called a geodynamo, and it has been running more or less continuously for at least 3.5 billion years. It is not a simple system. The fluid motion of the outer core is turbulent, unpredictable at small scales, capable of producing local instabilities that ripple outward into the broader field. The field it generates is not a clean dipole. It is lumpy, uneven, stronger in some places and weaker in others, and it drifts. The magnetic poles are not fixed at the geographic poles. They wander. They have always wandered. That much was known. What was not known until recently is how fast that wandering can get. New research has established that changes in the direction of the magnetic field can occur 10 times faster than previous models predicted. The old assumption was that the field's large-scale direction shifted over centuries, gradually enough that the slow drift could be tracked, modeled, and anticipated with reasonable confidence. That assumption is wrong. The data now show that the field can shift direction at rates that compress centuries of expected change into decades. 10 times faster. That is not a refinement of the old model. That is a replacement of it. To understand why speed matters, think about what the field actually does. It deflects charged particles from the sun. It extends out into space in a structure called the magnetosphere, a teardrop-shaped bubble that pushes solar wind around the planet. When the field is strong and stable, the magnetosphere holds its shape and the protection is reliable. When the field weakens or shifts rapidly, the magnetosphere deforms. Gaps can appear. Radiation that would ordinarily be deflected gets through. This is not theoretical. Satellites already detect elevated radiation in regions where the field is locally weak. The question is what happens when those regions grow, or when the weakening becomes global. Over geological time, the field has reversed completely. The magnetic North Pole and the magnetic South Pole have swapped positions. This has happened hundreds of times in Earth's history, recorded in the alignment of iron-bearing minerals in ancient rock formations that locked in the field's direction when they solidified. The last full reversal was roughly 780,000 years ago. Before that, reversals happened on average every 200,000 to 300,000 years, though the intervals vary enormously. By that rough average, the planet is statistically overdue. That statement does not mean a reversal is imminent. The geological record is too irregular to support precise predictions, but it does mean the question is not idle. During a reversal, the field does not simply flip cleanly from one orientation to the other, it weakens first. The orderly dipole structure breaks down. The field becomes patchy and complex, with multiple magnetic poles appearing at different points on the surface. The overall field strength can drop to as little as 10% of its normal value. At that point, the protection against solar wind and cosmic radiation is dramatically reduced. The atmosphere is not stripped away in years or decades. That process takes far longer, and Earth's gravity holds most of the atmosphere regardless. But over thousands of years of reduced shielding, the upper atmosphere erodes faster. Surface radiation levels rise. The biological and technological consequences of elevated radiation exposure are not trivial. Species that survive using magnetic navigation, birds, sea turtles, certain fish, would face serious disorientation. Power grids, communications satellites, and GPS systems that depend on predictable field geometry would face increasing stress. The Lachance excursion, roughly 41,000 years ago, gives a partial preview. The field dropped to about 20% of its current strength for several thousand years without completing a full reversal. Ice core records from that period show evidence of increased cosmogenic isotopes, atoms created when cosmic rays hit the atmosphere, confirming that more radiation was reaching the surface. Some researchers have linked the Lachamps excursion to extinctions among large mammals in Australia, though the connection remains debated. What is not debated is that the excursion happened, the field weakened significantly, and the planet's shielding was compromised for a substantial period. The new finding about field direction changing 10 times faster than expected does not predict a reversal. It says something more fundamental, that the assumptions built into every previous model of how quickly the field can change were too conservative. The outer core is capable of faster dynamics than the models assumed. Whatever drives rapid changes, sudden shifts in the pattern of fluid motion, instabilities at the boundary between the outer core and the mantle, those processes can operate on timescales that were previously considered impossible. The field is not the slow geological scale constant that scientific intuition had accepted. It is faster, more volatile, and less predictable than the models were built to accommodate. The most visible evidence of that instability is concentrated in one region, southwest of Africa, where the field has been weakening for decades and where the rate of weakening has accelerated since 2020. That speed matters because the same field that keeps solar radiation from stripping the atmosphere bare is now changing on timescales that nobody had built into the models. Southwest of Africa, in a region of the South Atlantic that most people will never visit and almost nobody thinks about, Earth's magnetic field has a wound. It is not a metaphor. The magnetic field has real structure, regions of strength and regions of weakness, and in this particular stretch of ocean, the field is measurably, dramatically weaker than it should be. Scientists call it the South Atlantic Anomaly. It stretches from roughly the southern tip of South America across the Atlantic and into the southern edge of Africa, covering an area larger than most continents. And for decades, the field strength inside it has been declining. To understand why this matters, you have to understand what the magnetic field actually does. The field is generated deep in the planet, in the churning liquid iron of the outer core, and it extends outward into space, forming a protective bubble around Earth. That bubble deflects solar wind, the constant stream of charged particles pouring off the sun, and filters out cosmic radiation from deeper in the galaxy. Without it, those particles would hit the upper atmosphere directly. Over long timescales, they would strip it away. The field is not a convenience. It is the reason the atmosphere exists at all. In the South Atlantic Anomaly, that protection is thinner. The field strength in this region runs at roughly a third of what you would measure at the same latitude on the opposite side of the planet. Particles that would normally be deflected are getting through. The consequences are practical and immediate. Satellites crossing the anomaly are exposed to elevated radiation levels that can corrupt electronics, scramble memory, and shorten operational lifespans. The International Space Station shields its systems when it passes through. Engineers who design satellite orbits account for it the way you would account for a stretch of rough road. It is a known hazard on a map that everyone in the field carries. The ESA launched the Swarm mission in 2013 specifically to map the magnetic field with the highest precision ever attempted. 3 satellites flying in coordinated formation, measuring field direction and intensity continuously across the entire globe. The data they have returned between 2014 and 2020-14 and 2020-14 and 2020-25 tells a clear story. The South Atlantic Anomaly has been expanding steadily. Its boundaries have pushed outward. Its minimum field strength has been dropping. And since 2020, a subregion within the anomaly, a smaller zone off the southwest African coast, has been weakening at a faster rate than the rest of the anomaly around it. A wound inside a wound. The leading explanation involves structures called reverse flux patches. These are regions at the boundary between the liquid outer core and the solid rocky mantle, a boundary nearly 2,900 kilometers below the surface, where the magnetic field direction is locally inverted. Instead of pointing in the same direction as the broader field, the field at these patches points the opposite way. The effect at the surface is that these patches reduce the overall field strength in the regions above them, the way a countercurrent weakens a river's flow. The South Atlantic Anomaly sits above an unusually dense concentration of these patches. Something in the dynamics of the core mantle boundary beneath the South Atlantic is generating and sustaining this configuration. What exactly is doing that, and why it is doing it there rather than somewhere else, is a question the models have not cleanly answered. What the data does show is acceleration. Before 2020, the anomaly was growing, but at a pace that felt measured, almost geological. Since 2020, the inner core of the weakening has been dropping faster. The rate of change has increased. Whether that is a temporary fluctuation in the core dynamics or the beginning of a more rapid phase is not established. It is being watched very closely. For technology, the practical stakes are already real. Low Earth orbit satellites cross the anomaly on most of their orbits, depending on inclination. The increased radiation dosing over time degrades electronics, affects sensor accuracy, and in some cases causes unrecoverable errors. GPS satellites operate at higher altitudes and are less directly affected, but the downstream effects of a weakening field on the ionosphere, the charged layer of atmosphere that GPS signals pass through, introduce errors that have to be compensated for. Ground-based systems near the anomaly, in countries like Brazil, Argentina, and across southern Africa, face elevated exposure to geomagnetically induced currents during solar storms. Power infrastructure in these regions is more vulnerable when the shield overhead is thinner. The deeper question is whether the anomaly is a local feature or a symptom. Earth's magnetic field reverses on geological timescales. The north and south magnetic poles swap positions completely. The geological record shows this has happened hundreds of times in Earth's history. The last full reversal was roughly 780,000 years ago, during a period geologists call the Brunhes-Mutuyama reversal. The average time between reversals over the past few million years has been around 200,000 to 300,000 years. On that schedule alone, the planet is overdue. A reversal does not happen overnight. It unfolds over thousands of years, with the field weakening globally, becoming complex and multipolar, multiple north poles, multiple south poles appearing at different locations simultaneously, before eventually settling into a new stable orientation. During the transition, the protection provided by the field would be significantly reduced everywhere, not just in the South Atlantic. The atmosphere would not disappear. The timescale for atmospheric erosion is far longer than a reversal event, but radiation reaching the surface would increase. Navigation systems that depend on the field's orientation would require continuous recalibration. The biological effects over thousands of years are an open area of research. The honest answer to whether the South Atlantic Anomaly is an early sign of a coming reversal is that nobody knows. Some researchers point to the fact that the field has been weakening globally for about 160 years, not just in the anomaly, and that the presence of multiple reverse flux patches is a pattern associated with the early stages of field instability. Others argue that the geological record contains many episodes of field weakening and anomalous behavior that did not lead to full reversals, that the field self-corrected, and there is no reliable way to tell from the current data which scenario applies. The anomaly could stabilize, the reverse flux patches could dissipate, the field could recover. Whether that question is urgent or merely academic depends on how fast the wound is deepening, and since 2020, it has been deepening faster than before. For billions of years, the moon has been the dominant force shaping how Earth rotates. Its gravitational pull has been slowly applying the brakes, stretching Earth's day by tiny fractions of a second over geological time. This has been one of the most reliable relationships in planetary physics, as dependable as any force in the solar system. Then something changed. A new study from researchers at ETH Zurich found that the primary driver of changes to Earth's rotation is no longer the moon. It is us. More precisely, it is the water we have been releasing from ice sheets and glaciers by warming the planet. That finding is not a footnote. It is a rearrangement of the hierarchy of forces that govern how this planet moves. To understand what polar drift actually is, you need a clear picture of what the geographic poles represent. They are not magnetic features. They are the 2 points on Earth's surface where the planet's rotation axis intersects the ground. Everything spins around those 2 points, and those points move. This is not a new discovery. Scientists have known for over a century that the poles drift slowly across the surface, tracing irregular paths across the polar regions. What is new is the speed, and what is driving it. For most of recorded history, polar drift was slow enough that it was mainly a curiosity for geodesists, scientists who measure Earth's shape and position with extreme precision. Now it has become something that the entire architecture of global positioning has to account for. The physics behind this is the same physics that governs a figure skater spinning on ice. When a skater pulls their arms inward, they spin faster. When they extend their arms outward, they slow. This happens because of a property called the moment of inertia, the resistance of a rotating object to changes in its rotation, which depends on how mass is distributed relative to the axis of spin. Earth works the same way. When ice accumulates near the poles, mass is concentrated close to the rotation axis. When that ice melts and the water spreads across the world's oceans, mass moves away from the poles and toward the equatorial regions. That redistribution changes the planet's moment of inertia, and when the moment of inertia changes, the rotation axis shifts to compensate. The poles move. What the ETH Zurich research quantified was how much. Their projections show that Earth's poles could shift by more than 89 feet between now and 2100. That is not a rounding error. That is a detectable consequential displacement of the points around which the entire planet rotates. And the primary engine driving that displacement is the accelerating loss of ice from Greenland, Antarctica, and glaciers around the world. The pace of ice loss has been increasing. The faster the ice melts, the faster the mass redistribution, and the faster the pole moves. Here is where the finding becomes harder to absorb. For billions of years, the moon was the uncontested dominant influence on Earth's rotational dynamics. It was more powerful than any geological process, any atmospheric change, any redistribution of water. That was simply the physical reality. The new research concludes that human-driven climate change has now overtaken the Moon's influence as the primary driver of changes to Earth's rotation. The melting ice sheets are moving more mass, more quickly than the tidal forces the Moon exerts. That is the kind of statement that requires a moment. The gravitational relationship between Earth and the Moon has been the dominant rotational influence on this planet since the early solar system. That relationship is now being outcompeted by the consequences of burning fossil fuels. Researchers can actually observe the polar drift directly. Precise geodetic instruments track the position of the poles to within centimeters. Satellite data confirms what ground-based measurements show. The poles have been drifting eastward at an accelerating rate since the 1990s, which corresponds closely with the period when ice loss from Greenland and Antarctica began accelerating. The correlation is not coincidental. The timing matches, the physics matches, the mechanism is understood, even if its long-term behavior is not fully characterized. What makes this practically significant, beyond the physics, is what it means for the systems that modern civilization depends on. The global positioning system and every equivalent network are calibrated against a set of reference frames. Those frames are anchored to assumptions about where Earth's rotation axis sits. GPS does not simply bounce a signal off a satellite and report a location. It triangulates against a precise model of the planet's geometry. When the poles drift, that geometry changes. Engineers who maintain GPS systems update the reference frames periodically to account for this. But the updates are based on measured drift, which always lags behind the actual movement. The faster the poles move, the larger the gap between the reference frame and reality becomes at any given moment. For most applications, this gap is small enough to manage, but precision navigation, the kind used in aviation, automated shipping, and scientific measurement, requires extremely tight positional accuracy. A drift of 89 feet in the pole position by 2100 translates into reference frame corrections that grow in magnitude with each passing decade. The systems built to track Earth's exact orientation are sophisticated enough to handle this. What they were not designed for was a rate of change that keeps accelerating. The models those systems were built against assumed a world where the dominant forces on Earth's rotation were geological and lunar, slow, predictable, bounded. That assumption held for a very long time. The reference frames that underpin every GPS system on the planet assume a degree of rotational stability that Earth is quietly in the process of abandoning. Earth's axial tilt, the 23.5-degree lean that gives us summer and winter, that determines how much sunlight falls on each hemisphere and when, shifted in 2024 by roughly 80 centimeters. That number sounds almost absurd. 80 centimeters, less than the height of a kitchen counter, against the scale of a planet nearly 13,000 kilometers wide. It is nothing, except that it is not nothing. It is a measurable displacement of the axis around which the entire planet rotates, and it was detected outside the range of variation that scientists expected to see. To understand why this matters, you have to understand what axial tilt actually controls. The 23.5-degree angle is not some fixed property of the planet. It is the result of forces acting on Earth's orientation over time, the gravitational pull of the Moon, the Sun, the other planets, and the distribution of mass across the planet's own body. That angle sets everything about the seasons. It determines how directly sunlight strikes the northern hemisphere in June and the southern hemisphere in December. It controls how far north the sun rises in summer and how low it hangs in winter. Change the angle, and you change how solar energy is distributed across latitudes. Change how energy is distributed, and you shift the conditions that drive weather systems, ocean currents, ice coverage, and precipitation patterns. The tilt is not a detail. It is one of the fundamental inputs to the climate system. So when a 2024 study reported that the tilt had shifted by approximately 80 centimeters, researchers paid attention. The displacement was real, it was measurable, and it was larger than what a natural background variation would predict at that moment. Something had moved mass, or changed the forces acting on Earth's orientation, or both. The leading candidate is ice melt. When glaciers and ice sheets lose mass, that water doesn't disappear, it redistributes into the oceans. Mass that was sitting at high latitudes, near the poles, moves toward lower latitudes and spreads across ocean basins. This changes the planet's moment of inertia, the same way shifting weight on a spinning top changes the angle at which it tilts. Earth is not a rigid sphere. It responds to mass redistribution. The poles drift, as the previous observations confirmed, and under the right conditions the tilt itself shifts. The sheer volume of ice that has melted in Greenland and Antarctica over recent decades represents an enormous transfer of mass, and the physics says that transfer has to show up somewhere in the planet's rotational behavior. The 2024 shift may be part of that signal. Atmospheric pressure changes are also under consideration. Large-scale shifts in how air masses are distributed across the planet can exert small but measurable torques on the planet's orientation. These effects are generally much smaller than those driven by ice melt, but in combination they could contribute to a cumulative displacement. The honest answer is that the full accounting of what drove the 2024 shift has not been completed. Here is where it gets complicated. Earth's axial tilt does not stay fixed even under purely natural conditions. Over cycles of roughly 41,000 years, the tilt oscillates between about 22.1 and 24.5 degrees. These are the Milankovitch cycles, and they have been driving long-term climate variation for hundreds of millions of years. Ice ages have come and gone in part because of these slow oscillations. Scientists have mapped these cycles in extraordinary detail. They know where in the cycle Earth currently sits, and they know what the tilt is expected to be doing right now. What the 2024 study found was a shift that did not match the expected trajectory. It was not explained by the background oscillation. It was additional. That is what made it significant. To detect a genuine departure from expected behavior, you have to rule out the natural signal. This is not trivial. The measurement tools involved, geodetic satellites, very long baseline interferometry arrays, precision GPS networks, have become sensitive enough to resolve changes at the centimeter scale in Earth's orientation. This kind of precision was simply not available to earlier generations of scientists. We are only now able to detect signals that may have been occurring for some time without anyone having the instruments to see them. That cuts both ways. It means the 2024 shift might be a genuine departure. It also means that without a long baseline of equally precise measurements, distinguishing a new trend from an unusual single observation is difficult. What is not in doubt is that the physical mechanisms capable of producing this kind of shift are currently active and intensifying. Ice melt is accelerating. Mass is being redistributed at rates that have no modern precedent. The forces acting on Earth's orientation are not static. They are changing, and they are changing faster than the natural background cycles that scientists have used for decades as the baseline for what counts as normal. 80 centimeters is not the end of a story. It may be the beginning of one, or it may close out as an anomaly, a year when several factors lined up in a particular direction and then resolved. Science does not yet have the answer. Whether the 2024 shift is a momentary fluctuation or the first data point in a new trend is something scientists are still working to determine. In 2023, ocean surface temperatures began doing something that the best monitoring systems on Earth had not anticipated. The numbers started climbing in the spring and kept going. By the summer, sea surface temperatures had broken every record in the instrumental record, not by fractions but by margins that stopped researchers mid-sentence. Scientists who had spent careers tracking ocean warming described the data as, in their own words, shocking. That word does not appear often in peer-reviewed literature. It appeared in 2023. To understand why the spike was so alarming, you have to understand what the ocean actually does with heat. The oceans absorb more than 90% of the excess energy that accumulates in the climate system. Every watt of heat that the atmosphere traps and cannot release goes somewhere, and that somewhere is overwhelmingly the sea. The ocean is the planet's thermal buffer. It is the reason Earth does not swing between temperature extremes the way a desert does between day and night. Without the ocean absorbing heat at this scale, surface air temperatures would be dramatically higher than they already are. The ocean has been doing this quietly for decades, absorbing the consequences of an atmosphere loaded with greenhouse gases, holding the heat in its upper layers and cycling it slowly into the deep. What happened in 2023 was that buffer showed something unexpected. Part of the story was predictable. El Niño conditions returned in 2023, and El Niño always pushes ocean temperatures higher. It suppresses the upwelling of cooler deep water in the Pacific, allowing surface temperatures to climb. Anthropogenic warming was continuing its steady background trend. Add these two together and you would expect record temperatures. Researchers expected record temperatures. What they did not expect was records broken by this much. The gap between what the models projected for a strong El Niño year and what the instruments actually recorded was wide enough that El Niño and background warming combined could not account for it. Something else appeared to be contributing. One candidate was the Hunga Tonga eruption. In January of 2022, a submarine volcano in the South Pacific erupted with a force that sent shockwaves around the planet multiple times. It was one of the largest eruptions in the modern instrumental record. What made it unusual was not just its force, but what it injected into the atmosphere. Most volcanic eruptions push sulfur dioxide into the stratosphere, which reflects sunlight and temporarily cools the planet. Hunga Tonga did that too, but it also injected an extraordinary amount of water vapor. Estimates suggest it increased total stratospheric water vapor by somewhere between 10 and 15%. Water vapor is itself a greenhouse gas. Some researchers proposed that this stratospheric water injection was amplifying the greenhouse effect enough to push ocean temperatures beyond what El Niño and baseline warming alone could explain. The timeline lined up. The physics was plausible. Not everyone agreed. Critics pointed out that the Hunga Tonga effect, while real, was likely too small to account for the full anomaly. The stratospheric water vapor would dissipate over years. The warming signal in 2023 was too large and too fast to be explained entirely by a single eruption 18 months prior. The debate was not resolved by the end of the year. It is still not resolved. What makes this scientifically uncomfortable is that the unexplained portion of the 2023 spike is not tiny. It is substantial enough that researchers cannot simply attribute it to noise. Meanwhile, a separate process was deepening quietly beneath the surface. The ocean is stratifying. As surface waters warm, they become less dense relative to the cooler water below, and the boundary between warm surface layers and cold deep water grows more stable, more resistant to mixing. Think of it as a lid tightening on a pot. The warm layer sits on top, and what lies beneath becomes increasingly isolated. This matters enormously for ocean biology. Cold, deep water carries nutrients upward when it mixes with the surface. Nitrates, phosphates, the chemical building blocks that drive phytoplankton growth. Phytoplankton are the base of the marine food web. Less mixing means less upwelling, which means less nutrient delivery to the sunlit surface layers where photosynthesis happens. Fisheries that depend on productive upwelling zones are already showing signs of this stress. The food chains built on phytoplankton productivity extend from microscopic organisms all the way to the largest marine mammals on the planet. Stratification also affects oxygen. The deep ocean gets its oxygen from surface mixing. As the surface warms and stratification intensifies, oxygen delivery to deep water slows. Low oxygen zones in the ocean, dead zones in practical terms, have been expanding for decades. Marine species that cannot tolerate low oxygen have nowhere to go. The deep ocean is not a backup habitat. It is a connected system that depends on the surface to breathe. The full picture coming out of 2023 was not just that temperatures were high, it was that multiple consequences were unfolding simultaneously. Record surface temperatures, stratification intensifying, deep water losing oxygen, nutrient upwelling declining. The El Niño pattern that scientists had used to frame their expectations turned out to be insufficient as an explanation for the magnitude of what was observed. Researchers continued publishing, continued revising their models, continued trying to close the gap between what was predicted and what was measured. That gap has not been fully closed. Some researchers believe it will close as more data comes in and the Hunga Tonga contribution gets better quantified. Others believe the models themselves are missing something, a feedback, a process, a coupling between systems that the equations haven't captured yet. The honest position, the one that emerges from the scientific literature rather than from any press release, is that 2023 showed the ocean doing something that existing frameworks did not fully anticipate, and the explanation is still being assembled. The most uncomfortable possibility, that the ocean is warming faster than our best models predicted, has not been ruled out. In April of 2024, NOAA announced something it had never announced before. For the fourth time in recorded history, a global coral bleaching event was underway. Not regional, not confined to one ocean or one hemisphere. Every major reef system on the planet was bleaching at the same time. That had never happened before on this scale, and scientists who had spent careers studying coral reefs described the moment with a kind of quiet dread that doesn't translate well into press releases. To understand why this matters, you need to understand what a coral actually is. The structure you see, the branching, rocky, colourful architecture of a reef, is built by tiny animals called coral polyps. These polyps cannot survive on their own. They depend on microscopic algae called zooxanthellae, which live inside their tissue. The algae photosynthesize, producing sugars that feed the coral. In return, the coral provides shelter and the compounds the algae need to function. It is one of the most productive partnerships in the natural world. The color you associate with healthy coral, the yellows, oranges, purples, deep greens, comes almost entirely from the algae. When ocean water gets too warm, that partnership breaks down. Even a rise of 1 degree Celsius above the seasonal maximum, sustained for several weeks, causes the coral to expel the algae. The tissue turns transparent, revealing the white calcium carbonate skeleton beneath. That is what bleaching looks like. The coral is not dead yet, but it is starving. Without the algae, it has no food source. A bleached coral can survive if temperatures drop quickly enough. The algae can return, the partnership can be re-established. But if the heat persists, the coral dies, and what remains is a white skeleton that gradually gets covered in algae of a different kind, the kind that signals a reef in collapse. The 2024 event was the 4th global bleaching event ever documented. The first was in 1998, the second in 2010. The third ran from 2014 to 2017 and was the longest and most severe ever recorded at the time. Now a fourth. The interval between the first and second was 12 years. Between the second and third, 4 years. The fourth began less than 7 years after the third ended. The gap is closing. That pattern is not subtle. It is measurable, directional, and it reflects the underlying trend in ocean temperature that the previous section described. Reefs are not hitting a single catastrophic event and trying to recover. They are being hit repeatedly at increasing frequency before the previous damage has healed. The scale of what reefs represent makes this more than an ecological concern. Coral reefs cover less than 1% of the ocean floor. They support approximately 1/4 of all known marine species. That ratio is one of the more startling numbers in biology. 1% of the habitat, 25% of the species. Reefs are the tropical rainforests of the ocean, extraordinarily dense concentrations of biodiversity packed into a relatively small physical space. Remove the reef structure, and you remove the habitat that hundreds of thousands of species depend on for shelter, breeding grounds, and food. The human dimension is just as significant. Somewhere between 500 million and 1 billion people worldwide depend on coral reefs directly for food, income, or coastal protection. Reef fisheries provide protein for communities across the Indo-Pacific, the Caribbean, and East Africa that have no ready alternative source. The physical structure of a reef also acts as a buffer against wave energy, reducing coastal erosion and protecting shorelines from storm surge. When a reef dies and the calcium carbonate skeleton erodes, that protection disappears. Coastlines that were stable for centuries become vulnerable. The economic value of what reefs provide in fisheries, tourism, and coastal protection is estimated in the hundreds of billions of dollars annually. That value is not evenly distributed across wealthy nations that can absorb its loss. It falls disproportionately on some of the poorest and most geographically exposed communities on Earth. What makes the 2024 event scientifically distinct from the 3 that preceded it is the simultaneity. Previous global events were called global because they affected multiple ocean basins, but the severity was uneven. Some regions were hit hard while others experienced moderate stress. In 2024, the bleaching signal was registering across the Atlantic, Pacific, and Indian Oceans at the same time, with significant severity in regions that had previously been considered more resilient. Reefs in the Florida Keys, the Great Barrier Reef, reefs across the Central Pacific and the Arabian Sea, all showing bleaching simultaneously. That kind of synchronized stress across the entire planet requires a globally elevated baseline temperature. It is not the signature of a localized event. It is the signature of an ocean that is warmer everywhere. The recovery problem is where the long-term trajectory becomes hardest to look at directly. After the 1998 bleaching event, many reefs recovered over the following decade. The 2010 event caused damage that took longer to reverse. After the 2014 to 2017 event, some reefs had not reached full recovery before ocean temperatures spiked again. Recovery is not instantaneous. Coral growth is slow. A branching coral colony might grow a few centimeters per year under good conditions. Rebuilding a reef structure after significant mortality takes decades. Reefs can recover from bleaching events if those events are spaced far enough apart. The question that researchers are now actively investigating is whether the spacing has already become too short in some regions for recovery to outrun the next event. Some scientists have begun describing a threshold concept, a frequency of bleaching above which reefs cannot rebuild between events and begin transitioning to systems dominated by algae rather than coral. Whether that threshold has already been crossed in parts of the Caribbean or the Indo-Pacific is not a settled question. The data are being analyzed. The answers are not yet in. For some reefs, the question of whether they can recover before the next bleaching event is no longer hypothetical. Running up the length of the Atlantic Ocean, from the tropics to the North Atlantic, is a river of warm water that moves more water than all the rivers on Earth combined. It has no banks, it has no visible surface, but it is one of the most consequential physical systems on the planet, and it is slowing down. Scientists call the full system the Atlantic Meridional Overturning Circulation, or AMOC. The Gulf Stream is its most recognizable piece, the fast, warm current that runs up the eastern coast of North America before swinging northeast toward Europe. But the Gulf Stream is only one part of a much larger loop, and that loop is the thing that matters. Here is how it works. Warm, salty water from the tropics flows northward along the surface of the Atlantic. As it moves into the North Atlantic, it releases heat into the atmosphere. This is why Western Europe has a climate far milder than its latitude would suggest. London sits at roughly the same latitude as Calgary. Without AMOC, it would feel much more like Calgary. As the surface water gives up its heat, it cools. Cold water is denser than warm water. Dense water sinks. It drops thousands of meters to the ocean floor and then flows south as a deep, cold current running all the way to the Southern Ocean. Eventually, it warms, rises again, and the loop continues. The whole system is driven by one thing: the density difference between warm tropical water coming north and cold water in the North Atlantic sinking down. That density difference depends on temperature and salinity. And this is where the problem begins. As the ice sheets of Greenland and the Arctic melt, enormous volumes of fresh water pour into the North Atlantic. Fresh water is less dense than salt water. When it floods into the region where AMOC depends on heavy, sinking water, it dilutes the salinity, reduces the density, and weakens the downwelling that pulls the whole loop forward. Less downwelling means slower circulation. Slower circulation means less heat transported north. The mechanism by which the entire system could be undermined is already running. Measurements confirm it. Studies analyzing ocean sediment cores and sea surface temperature records suggest AMOC has slowed by approximately 15% compared to where it stood a century ago. That number represents a real and significant change in a system that civilization in the Northern Hemisphere has been built around. Europe's agriculture, its winters, the timing and geography of rainfall across the North Atlantic basin, all of it is calibrated to a world where this circulation runs at its current strength. The models predicted this weakening decades ago. The data now backs them up. What a further slowdown would actually mean is not abstract. Parts of northwestern Europe would experience significant cooling, even as global average temperatures continue to rise. The cooling would not be uniform and would not cancel out warming everywhere, but in regions that depend heavily on AMOC-driven heat delivery, the shift could be severe. Simultaneously, the disruption to atmospheric circulation patterns would reach beyond Europe. Monsoon patterns in West Africa and South Asia are connected to Atlantic circulation in ways that are still being mapped, but the links are real. A weakening AMOC shifts where and when rain falls across enormous portions of the planet. There is also a sea level dimension that is easy to overlook. AMOC currently acts as a kind of pump that pushes surface water away from the US East Coast. As the current moves water northward and offshore, it keeps sea levels along the American coastline somewhat suppressed. Weaken that pump, and the suppression weakens with it. Studies project that a significant AMOC slowdown would cause sea levels along the northeastern United States to rise faster than the global average, compounding the effects of overall ocean warming and ice melt on cities like Boston, New York, and Miami. The question that sits underneath all of this, the one that researchers argue about most intensely, is whether AMOC is capable of collapsing outright rather than merely slowing. Gradual weakening is serious. Collapse is a different category of event. Paleoclimate records show that AMOC has collapsed before. During the last ice age, abrupt circulation shutdowns called Dansgaard-Oeschger events caused temperature shifts of more than 10 degrees Celsius in Greenland within decades. These were not slow transitions. They were near instantaneous in geological terms. The possibility that AMOC has thresholds, tipping points beyond which the circulation doesn't slow progressively but reorganizes entirely into a different state, is not theoretical. It has happened. The argument is over whether current conditions are pushing toward one of those thresholds and how close we might be. This is where scientific consensus becomes contested. Some researchers, analyzing statistical signals in recent sea surface temperature data, have argued that AMOC may already be approaching a tipping point and could reach it within this century under current trajectories. Others dispute the methodology and argue the data is too noisy to support that conclusion. What is not disputed is that no one has identified a robust early warning signal that would give clear advance notice before a threshold is crossed. The physics of tipping points makes them difficult to detect from the inside. A system can appear to be changing gradually and then shift state very quickly once a threshold is passed. In 2024, AMOC remained weaker than its historical baseline and freshwater input from Greenland continued. No dramatic shift occurred. But the trend lines that have characterized the last century have not reversed. The circulation is not recovering. What the coming decades hold depends on factors that are still in motion: the rate of ice sheet loss, the trajectory of atmospheric warming, and the internal dynamics of a system that is complex enough that even the best current models cannot agree on exactly where its limits lie. The difference between a gradual slowdown and a full collapse is not a difference of degree. It is a difference that would rewrite the climate of entire continents within a human lifetime. There are rivers in the sky, invisible from the ground, that carry more water than the Amazon. They have no banks, no color, no surface you could touch. They are corridors of concentrated water vapor, sometimes thousands of miles long and only a few hundred miles wide, streaming out of the tropics and pushing into higher latitudes with enormous force. Most people have never heard the term. Meteorologists only began treating them as a distinct category of weather system in the 1990s. For most of human history, they were just storms, bad ones, unusually wet ones, and nobody had a framework for what was actually happening overhead when they arrived. The physics is straightforward once you see it. Warm air near the equator holds tremendous amounts of moisture. As tropical air masses move, they don't simply drift upward and disperse. In certain conditions, they get organized by pressure gradients and the planet's rotation into narrow, fast-moving streams. Think of squeezing a wide, shallow channel into something much narrower. The flow accelerates. The concentration of moisture per unit of width becomes extraordinary. A mature atmospheric river can carry as much water vapor in a single day as the Mississippi River carries past New Orleans in a year. That is not a rough estimate. That is what the measurements show. Seeing them required satellite technology that didn't exist until recently. From the ground, an atmospheric river looks like clouds, then rain, then more rain. From space, using infrared sensors that detect water vapor concentrations in the mid-atmosphere, the structure becomes visible. A long, bright plume stretching from somewhere near Hawaii or the Gulf of Mexico, arcing up toward a coastline like a fire hose pointed at a wall. Researchers at the Scripps Institution of Oceanography began systematically cataloging these features in the 1990s. The more they looked, the more consequential the structures turned out to be. Atmospheric rivers are now known to account for roughly 22% of all freshwater runoff globally. In the western United States, they are responsible for the majority of extreme precipitation events. In parts of Europe, they drive the winter floods that inundate river basins and overwhelm drainage infrastructure built for a different kind of rainfall. For years, the scientific consensus was that atmospheric rivers were powerful but bounded. They arrived, delivered their moisture, and moved on. The water they carried was enormous in aggregate, but the events were distinct, separated by intervals of recovery. That understanding is shifting. Warmer air holds more moisture. This is not a complicated principle. It follows directly from basic thermodynamics, and the specific relationship has a name: the Clausius-Clapeyron equation. For every degree Celsius of atmospheric warming, air can hold roughly 7% more water vapor. That number is small enough to sound harmless. Across the scale of an atmospheric river, it is not. If the air feeding a moisture plume is 2 degrees warmer than it was 50 years ago, that plume carries somewhere around 14% more water than a comparable event in the past. The storm doesn't have to get bigger. It doesn't have to travel farther or move faster. It just delivers more, because the air it's made of has more to give. Studies projecting future atmospheric river behavior under high emission scenarios found that the most extreme events could nearly double in frequency by the end of the century. The key word is extreme. The weak and moderate atmospheric rivers may not change as dramatically, but the top tier, the events that cause the damage, that overwhelm flood control infrastructure, that produce the images of highways turned into rivers and hillsides collapsing, those are the ones that intensify fastest. Under some projections, what currently qualifies as a once-in-20-year atmospheric river event becomes a once-in-10-year event, then closer to once-in-5, The infrastructure built against historical recurrence intervals has no answer for that kind of compression. The 2023 season in California made this concrete. Between late December 2022 and March 2023, a sequence of atmospheric rivers struck the state in near-continuous succession. At least 9 major events by most counts, some arriving before the damage from the previous one had been assessed. Communities in the Central Valley flooded. Mountain snowpack reached levels that created its own downstream problems when spring warming accelerated. Rivers ran at capacities that hadn't been recorded in decades. The total precipitation in some regions exceeded 200% of the seasonal average. California has always had wet winters driven by Pacific moisture. What happened in 2023 was categorically different in its persistence and its stacking. Event after event after event, each one drawing from an atmosphere that held more water than the historical baseline. Scientists studying the sequence noted that while El Niño conditions in the Pacific contributed, the moisture loading of the individual events was higher than El Niño alone explained. The Clausius-Clapeyron effect was visible in the data. The events were organized by the same pressure systems that have always steered Pacific storms toward the California coast, but they were carrying more. The 2023 sequence was not an anomaly in the sense of being random or inexplicable. It was the kind of event that the atmospheric river intensification literature had been describing for years. It arrived ahead of some of the most aggressive model timelines, but not outside the range of what researchers said was possible. What makes atmospheric rivers particularly challenging from a planning standpoint is their apparent normalcy right up until they aren't. The air looks like any other winter storm front moving in off the ocean. The rain starts, as rain often does. Then it doesn't stop. And when the totals accumulate over a week of continuous events, the scale of what just happened becomes clear. The sky offered no obvious warning that this was different. It rarely does. Under the projections that concern scientists most, the events that felt extraordinary in 2023 become closer to routine. In 2024, climate scientists began using a phrase that had previously seemed like hyperbole. Simultaneous extremes. Not just more disasters in a year, but more disasters in the same weeks, hitting different continents at the same time, all of them record-breaking, all of them demanding a response at once. This is the part of the story that doesn't show up cleanly in the temperature graphs or the precipitation totals. The numbers are bad, but the timing is what's new. El Niño conditions were already pushing the baseline upward when 2024 began. A warmer ocean surface means more energy moving into the atmosphere, more fuel for storms, more heat baking drought-affected regions, more moisture available for the systems that eventually drop it all at once. El Niño years have always been worse than average. What made 2024 different was that the baseline it was amplifying had itself shifted. El Niño on top of a warming trend is not the same as El Niño on top of a stable climate. The two effects don't add up linearly. They compound. A 2024 flood in a region that was already warmer and drier than its historical average behaves differently than the same storm hitting the same landscape 50 years ago. Wildfires burned across South America, southern Europe, and parts of Canada and the western United States at scales that exceeded projections written less than a decade ago. Floods destroyed infrastructure across Central Africa and Southeast Asia within months of each other. Droughts stretched across multiple continents simultaneously, straining agricultural systems that were already operating under pressure. Each of these events, taken individually, could be accommodated by the standard framework of disaster response. Taken together, they exposed a structural problem that emergency planners had understood in theory, but never had to manage at this scale. When one major disaster strikes, other countries can contribute resources, personnel, and equipment. When 4 or 5 are happening simultaneously across different continents, that mutual aid calculus breaks down. Every country that might otherwise send help is managing something at home. This is the compounding problem. It is not simply that the disasters are larger. It is that the global system built to absorb and respond to them was designed around a different distribution of events. More spaced out, more geographically isolated, more predictable in their rough timing. The infrastructure of international disaster response has assumptions baked into it, just like every other infrastructure system. Those assumptions are being tested now in ways that their architects did not anticipate. The insurance industry is feeling this more acutely than almost any other sector. Flood insurance, in particular, is built on a concept called the recurrence interval. A 100-year flood is not a flood that happens once a century. It is a flood with a 1% probability of occurring in any given year. That probability is calculated from historical data. When the historical data no longer reflects current conditions, the model fails. Events that carried a 1% annual probability based on 20th century records are now happening in some regions every 10 years, or faster. The actuarial tables that underpin flood insurance pricing in many countries were calibrated to a climate that no longer exists. Several major insurers have withdrawn from high-risk coastal and wildfire-prone markets entirely. Others have raised premiums to levels that make coverage effectively inaccessible for many homeowners. The financial system designed to distribute risk from extreme weather events is breaking down in regions where those events are now too frequent and too severe to be priced sustainably. Infrastructure faces the same problem from a different angle. A bridge, a levee, a stormwater system, a power grid, these are all designed to handle loads defined by historical climate data. The 100-year storm event becomes the design standard. Engineers build with margin, but the margin is calculated against what was expected, not what is now occurring. Levees that held for decades are overtopped by storms that exceed their design thresholds. Stormwater systems that drained cities reliably now back up because the rainfall intensity exceeds what the pipes were built to carry. Power grids stressed by heat waves that were once rare now face those conditions multiple times per summer. Replacing or upgrading this infrastructure is a project of decades, requiring capital and planning cycles that operate on different timescales than the accelerating change they're meant to address. The scientific picture behind all of this involves a question that researchers are actively wrestling with. The models that project extreme weather intensification have been getting better for decades. They incorporate more physics, higher resolution, longer historical baselines, and more sophisticated coupling between atmospheric and oceanic dynamics. And yet, the rate at which some categories of extreme events have intensified in recent years is running ahead of what those models projected for this point in time. Not by a dramatic margin, by enough to be noticed. The question researchers are asking is whether this means the models are capturing everything they need to capture. There are feedbacks in the climate system, interactions between components that amplify or dampen each other, and some of them may be operating faster than the models currently represent. Clouds, for instance, remain one of the most difficult components to simulate accurately. How clouds respond to warming affects how much additional warming occurs. Small errors in cloud physics propagate through decades of simulation. There are also potential interactions between warming-driven changes and natural variability that are not fully characterized. None of this means the models are wrong in any fundamental sense. They represent the best physical understanding available and have been validated against historical observations in rigorous ways. But science is not static. When observations consistently run slightly ahead of projections, the scientific response is to look harder at what might be missing, not to dismiss the discrepancy. The gap between what the models projected for this decade and what is actually being observed is not large enough to be alarming on its own, but it is large enough that researchers are asking whether something is being left out. In 2024, Southern California had more earthquakes than it had seen in over 3 decades. Geophysicist Lucy Jones of Caltech put a number to it. Since reliable records began in 1932, the region averaged 10 to 12 earthquakes of magnitude 4.0 or greater every year. For the 2 decades before 2024, that average had dropped to roughly 5. The ground had gone quiet. Then, in 2024, it didn't, with more than 3 months still remaining in the year. Southern California had already logged 13 quakes of magnitude 4.0 or greater. The region was back to its historical pace, and people noticed. The return to historical rates is not, on its own, alarming. Earthquake frequency fluctuates. Seismologists have always known that. Any given decade can run quieter or louder than the long-term average, without signaling anything meaningful about what comes next. What makes 2024 significant is not the number in isolation, it is the number in context. Southern California is one of the most densely populated, seismically active regions anywhere on Earth. More than 20 million people live and work above one of the most complex fault systems ever mapped. The infrastructure beneath those people, the water lines, the power grids, the hospitals, the bridges, was designed and maintained against a specific expectation of risk. That expectation was calibrated, in part, against the relatively quiet 20 years that just ended. To understand what makes the geology here so complicated, you have to understand that the San Andreas is not a single fault. It is a system. The main strand runs roughly 800 miles through California, separating the Pacific Plate from the North American Plate. The 2 plates are not moving apart or pressing together head-on. They are grinding sideways past each other, the Pacific Plate sliding northwest relative to North America at roughly 2 inches per year. That motion is not smooth. It catches. It locks. Stress builds along the fault and along dozens of parallel strands running alongside it. The Garlock Fault, the Elsinore Fault, the Newport Inglewood, the Puente Hills Thrust sitting directly beneath Los Angeles. Each one accumulates strain independently and interacts with the others through stress transfer. When one segment slips, even in a moderate earthquake, it redistributes stress to adjacent segments. Whether that redistribution brings those segments closer to failure or delays it depends on the geometry, the orientation, and the current stress state, none of which can be read directly from the surface. Seismic waves from earthquakes are the main tool scientists have to probe what is happening in these fault zones. When a quake occurs, instruments spread across the region record how the waves travel, how long they take, how the ground moves. Over decades, this data builds a detailed picture of where faults lie, how they are oriented, and how stress is distributed across the system. The picture is remarkably detailed. It is not detailed enough. There are sections of fault that are fully locked and accumulating stress at measurable rates. There are segments that have not ruptured in centuries. There are places where the two plates slide past each other relatively smoothly, releasing stress gradually. And then there are the places where the stress has been building quietly and has given no indication of what it intends to do next. The question that hangs over a year like 2024 is the one seismologists are most reluctant to answer publicly, because the honest answer is that they cannot answer it at all. Does an increase in moderate seismicity, the 4.0s, the occasional 5.0, mean that stress is being released gradually, lowering the odds of a larger rupture? Or does it mean that a fault system is becoming more active across the board, stress transferring between segments, the whole system waking up towards something bigger? Both interpretations are physically plausible. Neither one is provably correct in advance. Seismologists have been asking this question for as long as the discipline has existed. The data does not resolve it cleanly. What is known with certainty is what a major rupture would mean in this particular place. The southern segment of the San Andreas Fault, running from the Salton Sea northwest toward the Los Angeles Basin, is considered one of the most dangerous fault segments in North America. It has not produced a major earthquake in roughly 300 years. At the rate the plates are moving, that represents somewhere around 20 to 24 feet of accumulated strain waiting for release. A rupture of that segment, sometimes called the big one in discussions that feel both urgent and impossibly abstract, would affect the most populated region in the western United States. The shaking would last longer than most people have experienced. Secondary effects would cascade: fires from broken gas lines, failures in water distribution, disruption to transportation networks that Los Angeles depends on for basic function. None of this means the big one is coming in 2025. It does not mean the increased seismicity of 2024 is a precursor to anything specific. Seismology is precise about mechanisms and frustratingly silent about timing. The fault will rupture again. The physics guarantees it. When, this year, next century, somewhere in between, is a question the instruments cannot answer. The ground shakes when it shakes. Seismology can tell you a great deal about how earthquakes work, and very little about when the next one comes. Globally, 2024 was one of the quietest years for large earthquakes in 4 decades. Only 99 earthquakes of magnitude 6 or greater were recorded across the entire planet. The long-term average sits at roughly 150 such events per year. That gap is not trivial. It means 2024 produced about a third fewer large earthquakes than the planet typically delivers, the lowest count since 1982. And yet, Southern California, in the same 12 months, was rattling through its most seismically active year in over 3 decades. Both things are true simultaneously. That is not a contradiction to be resolved. It is an illustration of something fundamental about how seismic energy is distributed across the planet. The crust does not release stress evenly or on a coordinated schedule. One region can be unusually quiet while another runs hot, and the global average tells you almost nothing about what any particular place is about to do. The long-term statistics do hold reasonably steady when viewed across decades. The planet produces roughly 15 earthquakes of magnitude 7 or greater every year. It produces 1 or 2 events of magnitude 8 or above in most years. These numbers have remained consistent enough across the instrumental record that seismologists treat them as reliable averages. What varies is where those events occur and when. and in what clustering pattern. A year like 2024 sits near the low end of normal variation. It does not signal anything conclusive about what the years immediately following it will bring. The planet is not building towards something by running quiet. It is simply running quiet for now, the way any system with natural variability occasionally does. What the global statistics cannot tell you is what no seismologist has yet been able to determine: where the next major earthquake will strike, when it will arrive, how large it will be. This is not false modesty from a field still in early development. It is the honest state of a discipline that has spent decades pursuing a single practical goal and has not achieved it. Earthquake prediction, in the sense of identifying a specific location, magnitude, and time window with useful precision, remains beyond reach. The tools available to seismologists today are vastly more sophisticated than anything that existed 50 years ago. Dense global networks of seismometers track ground motion continuously. GPS stations measure the slow creep and deformation of fault systems in real time. Satellite radar detects millimeter-scale changes in ground elevation across entire mountain ranges. The data flowing into research centers every day would have been unimaginable to the scientists who first began mapping fault zones. And none of it has produced a reliable earthquake warning in the predictive sense, a signal that appears before the earthquake and says something large is coming. The search for precursory signals has been serious and sustained. Researchers have looked at electromagnetic anomalies in the crust and ionosphere, on the theory that stress in rock can generate electrical signals before fracture. They have measured radon gas emissions from wells and ground cracks, since radon release can increase as rock deforms under stress. They have analyzed changes in groundwater levels, animal behavior, and ground tilt near fault zones. Some of these approaches have produced results that looked promising in individual cases. A study would report an anomalous signal appearing before a significant earthquake. The problem, when researchers tested each method systematically against the full historical record, was consistency. The same signal type that appeared before one large event was absent before comparable events elsewhere. It appeared before small events too. It appeared before events that never came. No precursor type has passed the test of reliable, repeatable prediction with a false alarm rate low enough to be operationally useful. This is not a problem of insufficient effort or inadequate funding. It reflects something deeper about the physics of fault systems. Earthquakes initiate at the point where accumulated stress finally exceeds the frictional strength of a fault plane. That moment of failure is governed by conditions at scales far too small and deep to measure directly. The rock properties at the exact point of nucleation, the fluid pressure in cracks at depth, the microscopic roughness of the fault surface. These are the variables that determine when the fault breaks. None of them can be observed with the resolution that prediction would require. The Earth's crust is not transparent. The instruments measuring it are all on the outside. Some of the most sophisticated research currently underway focuses not on prediction, but on probability. Rather than identifying when a large earthquake will occur, these efforts attempt to characterize how the probability of a large event shifts over time and across regions based on smaller seismicity patterns, fault loading rates, and historical data. This is useful. It informs building codes, infrastructure investment, and emergency preparedness planning. But it is not prediction. A probability statement does not tell you whether the earthquake comes tomorrow or in 300 years. The contrast between what seismology can do and what it cannot is one of the sharpest in all of Earth science. The same seismic networks that cannot predict earthquakes can tell you within minutes where one occurred, how deep it was, what the fault geometry looked like, and how the energy radiated through the crust. The retrospective picture is extraordinarily precise. The perspective picture is almost entirely dark. What happens underground before a fault breaks is still, in the most important sense, invisible. The planet shakes on a schedule of its own and has never once sent a notice in advance. In a swampy inlet in northwestern Venezuela, a lightning storm has been running, with brief interruptions, for as long as anyone has kept records. It sits over the bog where the Catatumbo River empties into Lake Maracaibo, and it operates on a schedule that defies easy explanation. Between 140 and 160 nights per year, the clouds build over that specific patch of water and begin firing. Not occasionally, not in scattered bursts. The storm produces up to 40 lightning bolts every minute at its peak, and it does this with a consistency that has made the region the most lightning-dense place on Earth. Sailors used it for navigation centuries ago. They called it the Lighthouse of Maracaibo. It was reliable enough to steer by. That fact alone should give you pause. A lightning storm so predictable it functions like a beacon. Scientists have studied Catatumbo lightning for decades. The leading hypotheses point to a combination of local geography, methane emissions from the lake bed, and the particular way trade winds funnel warm, humid air into the basin from the Caribbean, colliding with cooler air draining off the Andes. Those conditions, the thinking goes, create the instability that feeds the storm. The geography is real, the methane is measurable, the wind patterns are documented. What researchers have not been able to do is fully account for why this specific location produces lightning at this specific frequency with this specific consistency, year after year, across centuries. The ingredients are known. The recipe, precisely assembled, still escapes a complete physical description. No model has successfully reproduced Catatumbo from first principles and then predicted its behavior in detail. The storm keeps running anyway, indifferent to whether science has caught up. Move from that to ball lightning, and the explanatory gap gets wider. Ball lightning has been reported across thousands of years and every inhabited continent. The descriptions are remarkably consistent. A luminous sphere, typically between golf ball and grapefruit size, glowing steadily, moving slowly through the air, sometimes passing through closed windows or solid walls, lasting anywhere from a few seconds to a minute before vanishing quietly or with a sharp pop. These accounts come from ordinary people, from trained meteorologists, from naval officers, from physicists who witnessed the phenomenon mid-experiment. In recent decades, some events have been captured on video. A 2012 observation in China recorded a ball of light roughly 5 meters across, drifting at low altitude, and was accompanied by spectroscopic data showing a mineral composition consistent with soil, suggesting whatever the object was, it originated from or interacted with the ground. And yet no one has reliably produced ball lightning in a laboratory. No unified physical theory of what it actually is commands broad scientific acceptance. The hypotheses range from microwave radiation trapped in plasma bubbles to oxidizing silicon nanoparticles to electrical vortices in the atmosphere. Each theory explains some observations and fails against others. The plasma models struggle to account for longevity. The silicon models struggle to account for the penetration through solid barriers. The electrical vortex models struggle to account for the spectroscopic signatures. ball lightning is not a fringe phenomenon dismissed by serious researchers. It is an observed, documented, repeatedly witnessed atmospheric event that science cannot currently explain. That is a different category of problem than something merely rare or understudied. Mammatus clouds are a different kind of puzzle. They appear as clusters of rounded, pouch-shaped lobes hanging from the underside of cumulonimbus clouds, usually in the aftermath of severe thunderstorms. They are unmistakable. Photographs of them circulate widely because they look wrong. The intuition is that clouds should billow upward, not hang downward in smooth, bulging sacs. Mammatus appear regularly enough that any serious storm chaser has seen them. Any meteorology textbook includes them. They are not rare and they are not dangerous. What they are, precisely at the level of physical mechanism, is still contested. The standard explanation involves descending pockets of cold, saturated air that sink below the cloud base and form the pouches through a process of evaporative cooling. That framework is broadly accepted. The problem is in the details. Different studies have proposed different dominant mechanisms: turbulent mixing at the cloud base, radiative cooling, instabilities driven by ice crystal sedimentation, and the evidence from field observations and laboratory experiments has not cleanly resolved which mechanism dominates, or whether the answer varies from storm to storm. A 2006 review published in a major atmospheric science journal catalogued over a dozen competing explanations for Mammatus formation and concluded that none of them fully accounted for all observed cases. Nearly 2 decades later, that conclusion has not been dramatically revised. What links Catatumbo lightning, ball lightning, and Mammatus clouds is not that they are mysterious in a theatrical sense. They are not unexplained because no one has looked. Each of them has been looked at carefully by serious people with good instruments for a long time. They are unexplained in the more uncomfortable sense. The looking has happened and a complete physical account has not emerged. The atmosphere is a system of extraordinary complexity, a thin shell of gas wrapped around a spinning planet, heated unevenly, disturbed constantly by the surface below, capable of producing tornadoes, supercells, auroras, sprites, and elves. Some of what it produces, science describes precisely. Some of it, science can characterize without fully explaining. And some of what it produces falls into a narrower category. Phenomena that are observed reliably, documented rigorously, and still without a complete mechanistic account that withstands full scrutiny. That gap is not a failure of atmospheric science, which has achieved extraordinary things. It is a reminder that the discipline is not finished. A planet with a fluid atmosphere 4 miles deep, operating across every climate zone simultaneously, does not give up all of its behavior to inspection. Some of it remains, after centuries of watching, genuinely open. Ball lightning, Catatumbo, Mammatus, each of them sits in the literature as an open question, observed but not fully understood, waiting for a complete explanation that has not yet arrived. The changes described in this video are not happening independently of each other. That is the part that keeps Earth scientists up at night. Not any single anomaly in isolation, but the fact that these systems are connected, and the connections run deeper and stranger than the models have always assumed. You can study the magnetic field separately from the oceans. You can study polar drift separately from the rotation rate, but the planet does not organize itself around the convenience of academic departments. It runs as one coupled system, and when one piece moves, others move with it in ways that are sometimes predictable and sometimes not. Start with the ice. Greenland and Antarctica are losing mass at rates that were not expected at this point in the century. That mass is redistributing into the oceans, and the redistribution changes the planet's moment of inertia. Think of a figure skater pulling her arms inward and spinning faster. The physics is the same. As water shifts from ice sheets near the poles into the broader ocean basins, the balance of the planet's rotation changes. The poles drift. The length of the day changes by fractions of milliseconds. These are measurable effects. They are being measured right now. But the redistribution doesn't stop there. The outer core of Earth is a churning ocean of liquid iron. Its movement generates the magnetic field, and the dynamics of that liquid are sensitive to the rotation of the planet above it. When the rotation rate changes, even slightly, the fluid dynamics inside the outer core respond. The precise relationship is still being worked out, but the coupling is real. Changes at the surface, driven by melting ice, propagate downward through the planet's layers until they reach a structure nearly 3,000 miles beneath your feet. The magnetic field you cannot see is connected to the glacier you are watching disappear. Now go the other direction. Ocean circulation carries heat from the tropics toward the poles. As that circulation weakens, and the Atlantic circulation has slowed roughly 15% over the last century, the distribution of heat changes. Regions that were warmed by that current receive less of it. The atmosphere above the ocean responds. Temperature gradients shift. Atmospheric circulation patterns that move storms and set the boundaries of monsoon systems begin to reorganize. Where rain falls changes. Where it doesn't fall changes. Rivers that fed into the ocean carry different volumes of fresh water at different times of year. That fresh water reaches the North Atlantic and dilutes the salt water there, reducing the density contrast that drives the very ocean circulation that started this chain. The loop is closed. Each change feeds the next. What makes this difficult is not that the loops are unknown. Most of them are documented. The problem is characterizing their behavior under conditions that have no historical precedent in the instrumental record. These feedbacks have been built into climate and Earth system models for years. But the models are calibrated against a history in which the changes were slower. The feedbacks operated over centuries or millennia. What is happening now is faster, and faster systems can behave in ways that slower versions of the same system never revealed. A feedback that was stable at one speed may not remain stable when the forcing accelerates. Here is a specific example. Atmospheric rivers, those narrow corridors of water vapor moving from the tropics into higher latitudes, are intensifying. The reason is partly that warmer air holds more moisture. But where that moisture ultimately falls depends on atmospheric circulation patterns, which depend on the temperature gradient between the tropics and the poles, which depends on how much ice is left at the poles, which depends in part on how much moisture arrived there as precipitation, which came from the atmospheric rivers. The system is its own input. What you put in changes the conditions that determine what comes out the next time around. The models that include these couplings are among the most computationally demanding things humans have ever attempted. They simulate the atmosphere, the oceans, the land surface, the ice sheets, the carbon cycle, and some of them now include the solid Earth beneath. Running a multi-century simulation on one of these models requires supercomputers running continuously for weeks. And when the results come back, they regularly produce numbers that surprise the researchers who built them. Not because the physics is wrong, but because nonlinear coupled systems generate emergent behavior that wasn't visible in the individual components studied separately. The whole behaves differently from the sum of its parts. This is where the honest scientific difficulty lives. It isn't that researchers don't know ice melt affects rotation, or that rotation affects the outer core, or that ocean circulation affects precipitation. They know all of this. The difficulty is that quantifying how much, at what speed, with what lag time, and toward what endpoint requires running models through conditions they were not designed to simulate, because those conditions didn't exist when the models were built. The current pace of change is, in some respects, the experiment itself. What this means in practice is that each phenomenon covered in this video is also a signal about every other phenomenon. The accelerating pole drift is not just a story about ice and rotation. It is a data point about what is happening in the fluid dynamics 3,000 miles down, which is itself responding to forces at the surface. None of these observations stands alone. They are chapters in the same story being written by the same system. The coupling between Earth's systems is real. It is documented, and it means that understanding any one of these changes in isolation is a little like trying to understand a conversation by listening to only one side of it. The honest list of things scientists currently cannot explain about Earth's behavior is longer than most people realize, not the list of things being studied, or the list of things partially understood, or the list of things awaiting better data. The list of things that currently have no adequate physical explanation. That list is long, and in 2024 and 2025 it got longer. Start with the ocean temperature spike of 2023. The oceans warmed that year beyond anything the instrumental record had ever captured. That much is settled. What is not settled is why the numbers came in as high as they did. Researchers accounted for El Niño. They accounted for the long-term warming trend driven by greenhouse gas accumulation. They factored in the 2022 Hunga Tonga volcanic eruption, which injected an extraordinary volume of water vapor into the stratosphere and may have amplified warming in ways still being quantified. After all of that accounting, the numbers were still higher than the models said they should be. Some scientists believe the remaining gap will close as the analysis matures. Others are less confident. The honest answer, right now, is that the 2023 ocean temperature spike is not fully explained. Something happened that the best current models did not capture, and researchers have not yet reached consensus on what it was. Move to the inner core. The rotation reversal was confirmed in 2023. Seismic wave data collected over decades showed that the inner core, which had been spinning slightly faster than the rest of the planet, slowed, stopped, and appears to have reversed its rotation direction. There is a leading hypothesis that the reversal results from a torque imbalance between the gravitational pull of the mantle and electromagnetic forces from the outer core's convecting liquid iron. That hypothesis is plausible. It is not confirmed. The data that would definitively test it does not yet exist, because the only instrument available for probing the inner core is the seismic wave, and seismic waves do not give clean answers. They pass through the core and emerge changed, but interpreting those changes requires assumptions about the core's structure that are themselves uncertain. The rotation reversal is real. Why it happened when it did, and what drives the timing, remains an open question. And then there is the shape deformation reported in early 2025, the discovery that the inner core's outer layer is developing visible bulges and depressions. This is barely studied. The pressures at the center of the planet should make large-scale deformation extraordinarily difficult. yet the seismic data shows it happening. There is no accepted explanation. The South Atlantic Anomaly has been weakening for decades. The suspected driver is the behavior of reverse flux patches at the boundary between the outer core and the mantle, unusual magnetic configurations that appear to be suppressing field strength in that region. That explanation is a reasonable hypothesis built on real observations. It is not a confirmed mechanism. The physics connecting core mantle boundary dynamics to the specific geometry and evolution of the anomaly is not fully worked out. And since 2020, the weakening in the anomaly's most active region has accelerated beyond what prior trend lines predicted. What changed in 2020 is not known. Whether the acceleration represents a temporary fluctuation or a shift in the underlying process has not been determined. The Swarm mission has produced some of the best magnetic field data ever collected, and that data has sharpened the picture of what the anomaly is doing without yet explaining why it is doing it faster. Consider the synchronization problem. In recent years, major extreme weather events have been clustering across distant regions in the same seasons, in ways that statistical analysis suggests are not fully explained by known climate patterns. Simultaneous droughts on multiple continents, concurrent heat events in regions that historically experienced heat extremes at different times, flooding sequences in separate ocean basins within the same months. Whether this clustering represents a real physical coupling between distant atmospheric systems or an artifact of a warming baseline that pushes multiple regions over extremes at once is genuinely contested. Some researchers see a signal that current models are not fully capturing. Others argue the pattern falls within expected statistical range. The debate is unresolved. The Atlantic meridional overturning circulation sits in the same category. Researchers agree it has slowed by roughly 15% over the last century. Researchers agree it could slow further. Whether it is approaching a tipping point beyond which the circulation reorganizes abruptly rather than gradually is one of the most consequential and most contested questions in climate science. The models disagree with each other. The proxy records from ocean sediments suggest the circulation has collapsed before in Earth's history. But what triggered those collapses and how closely current conditions resemble those trigger states is not settled. The answer to the question of how close AMOC is to a critical threshold is, right now, genuinely unknown. That is not a hedge. That is the state of the science. None of this is an argument against the scientific enterprise. The opposite is true. Science has produced the instruments, the observation networks, and the analytical frameworks that allow these questions to be asked with precision. A century ago, the inner core's rotation could not be measured. The South Atlantic Anomaly could not be mapped in real time. Ocean temperatures at depth could not be tracked globally. The fact that these questions are visible is itself a product of scientific progress. What makes the current moment unusual is not that these questions exist. Open questions are the normal condition of a working scientific field. What makes this moment unusual is the density of open questions, the fact that they are not isolated to single subdisciplines, and the fact that several of them touch systems that are coupled to each other. An unexplained acceleration in the South Atlantic Anomaly is connected to questions about the inner core. An unexplained ocean temperature spike is connected to questions about atmospheric circulation and ice dynamics. The gaps in understanding are not neatly separated. They overlap in ways that make the uncertainty compound. What is unusual about the current moment is not that open questions exist in Earth science. It is how many of the open questions are active and pressing at the same time. In the physics of complex systems, there is a category of behavior called a tipping point, and it does not work the way intuition suggests. Most people picture a threshold as something you can feel approaching, a gradual build-up, a warning, the sense that you are getting close. Tipping points in Earth's physical systems do not work that way. A system can absorb pressure for decades and show almost no sign of strain. Then, at some unmarked threshold, the behavior flips. Not gradually, quickly. And once it flips, external conditions no longer control what happens next. The system drives itself. This is the property that makes tipping points genuinely different from ordinary change. Ordinary change is proportional. Push harder, get more change. Stop pushing, change stops. A tipping point breaks that relationship. Beyond the threshold, the forcing that caused the change becomes irrelevant. The system has its own momentum now. Permafrost is one of the clearest examples. Permafrost is ground that has stayed frozen for thousands of years across Siberia, Alaska, and northern Canada. Locked inside it is an enormous quantity of organic carbon, dead plant material that never fully decomposed because the ground was always frozen. When permafrost thaws, that material begins to decompose. Decomposition produces methane and carbon dioxide. Both are greenhouse gases. They warm the atmosphere. A warmer atmosphere thaws more permafrost. More permafrost releases more carbon. The loop closes on itself, and there is no obvious stopping point built into the physics. That is not a hypothesis. Permafrost thaw is already underway and already releasing carbon at measurable rates. The question is whether the release is still in a regime where it responds to external temperature, or whether it has crossed into self-sustaining territory. Scientists do not agree on the answer. That uncertainty is not a failure of the science. It reflects a genuine difficulty. These systems do not announce their thresholds in advance. You know you have crossed one when the behavior changes, and by then the crossing is already behind you. Ice sheets operate on a similar logic. Snow and ice are highly reflective. They send solar radiation back into space rather than absorbing it. As ice melts, darker ocean or land surface is exposed beneath. Darker surfaces absorb more heat. More heat melts more ice. The technical term for this is ice albedo feedback, and it is not controversial. It is measured. What remains uncertain is at what point the feedback becomes strong enough to sustain further melting without additional atmospheric warming. Parts of the West Antarctic ice sheet may already be past that point. The bed beneath the ice slopes downward toward the interior, meaning that as the edge retreats, it exposes deeper and deeper ice to warmer ocean water. Several studies now describe this as potentially irreversible under current conditions. Potentially is doing significant work in that sentence. The science has not settled on certainty, but the direction of evidence is not reassuring. The Amazon represents a third distinct mechanism. The Amazon rainforest generates a large fraction of its own rainfall. Trees pull water from the soil and release it into the atmosphere through a process called transpiration. That moisture travels on wind currents and falls again as rain, often hundreds of miles to the west. The forest is, in a real physical sense, recycling its own water supply. Deforestation interrupts this cycle. Remove enough trees and rainfall in the interior drops. Reduced rainfall stresses the remaining trees. Stressed trees die or fail to transpire effectively. Less transpiration means less rainfall. The system degrades its own foundation. Some researchers estimate that between 17 and 20% of the Amazon has already been deforested. Studies suggest that somewhere around 20 to 25% may represent a threshold beyond which the eastern Amazon begins a transition toward a drier, savanna-like state. The current figure is close enough to that range to be uncomfortable. In 2022, a paper published in the journal Science identified 16 major tipping elements in Earth's climate system. These included the Greenland ice sheet, the West Antarctic ice sheet, tropical coral reef systems, the Amazon, the boreal permafrost zone, and the Atlantic meridional overturning circulation, among others. The paper's finding was not that all 16 were certain to tip. It was that several of them may already be approaching their thresholds at current levels of warming, and that some may have thresholds lower than previously estimated. The paper also introduced the concept of a tipping cascade. This is the idea that one tipping point being crossed can push another closer to its own threshold through the system couplings that make Earth a single interconnected mechanism rather than a collection of independent parts. Consider the sequence. Greenland melts faster, flooding the North Atlantic with fresh water. Fresh water disrupts the density gradient that drives the Atlantic circulation. The circulation weakens. Western Europe cools and experiences disrupted precipitation. The Amazon, which depends partly on Atlantic moisture, dries further. A drying Amazon approaches its own deforestation threshold faster. Meanwhile, reduced ice coverage in the Arctic changes atmospheric circulation patterns, pushing the jet stream into unusual configurations. Unusual jet stream behavior creates persistent weather extremes in mid-latitudes. Persistent drought accelerates land degradation. Each link in that chain is physically real. Whether they combine in that specific sequence, and on what timeline, is where the science remains genuinely uncertain. What is not uncertain is that tipping cascades are possible in principle, because the couplings between systems are documented. The debate is about proximity and timing, not about mechanism. No single tipping point being crossed is a guarantee of catastrophe. Systems that tip can stabilize at a new equilibrium. The new equilibrium may be stable. It will simply be different from the one that currently supports the conditions humans and most existing ecosystems evolved in. Multiple tipping points being crossed in sequence across a span of decades is a different scenario. The pace matters because it determines whether living systems have time to adapt. Past mass extinctions are partly characterized by the rate of environmental change outrunning adaptation. The deep time record on this point is not subtle. The researchers who study tipping elements are not, as a group, people given to dramatic overstatement. They tend toward careful language, precisely because the stakes of being wrong in either direction are high. What has changed in recent years is not the rhetoric, but the data. The observations from permafrost monitoring stations, ice sheet radar surveys, Amazon deforestation tracking, and ocean circulation sensors have collectively moved the tipping point discussion from something on the edge of mainstream climate science toward its center. The concern that researchers are increasingly reluctant to dismiss is not any single threshold being crossed, but what happens when several cross within a generation of each other. Earth has been through worse. That sentence is worth sitting with before anything else, because everything discussed in the previous sections, the slowing currents, the weakening magnetic shield, the drifting poles, the warming oceans, exists against a backdrop of planetary history so long and so violent that the current moment looks almost quiet by comparison. Earth is 4.5 billion years old. It has survived meteor impacts that vaporized entire ecosystems, volcanic eruptions that poisoned the atmosphere for millions of years, ice ages that buried continents under kilometers of ice, and magnetic reversals that left the planet with almost no protective field at all. The changes happening now are real, they are measurable, and they are accelerating. But they are not unprecedented in Earth's history, and that distinction matters. The last full geomagnetic reversal happened roughly 780,000 years ago, during a period geologists call the Brunhes-Matuyama transition. The planet's magnetic field weakened, fragmented into a chaotic pattern of competing poles, and then reorganized itself in the opposite direction over a span of thousands of years. Life continued. The oceans kept circulating. The atmosphere stayed in place. Earth navigated it, but the biosphere of 780,000 years ago was not this biosphere. The species alive then were not these species. The ecosystems, the climate zones, the distribution of forests and grasslands and coral reefs, none of it matches what exists today. The reversal didn't destroy life, it disrupted it in ways that played out over generations too long for any single species to observe. There is an older event worth understanding. Around 41,000 years ago, Earth experienced something called the Lachamps excursion. This was not a full reversal, but a dramatic temporary weakening and displacement of the magnetic field, during which the field strength dropped to roughly 5% of its normal value. For a period lasting perhaps 1,000 years, the planet was largely unshielded from solar radiation and cosmic rays. There is evidence in the ice cores, in the cave sediments, in the chemical signatures buried in ancient deposits, that something changed during this window. Some species that were present before the Lachamps excursion were gone afterward. Whether the field weakening caused those extinctions directly or contributed to them alongside other pressures is still being studied. What is clear is that a magnetic field that dropped to 5% of normal strength was not neutral for the life living under it. Go further back. Roughly 55 million years ago, during a period known as the Paleocene-Eocene thermal maximum, or PETM, Earth's average temperature rose by somewhere between 5 and 8 degrees Celsius in a geologically brief window, possibly as short as 20,000 years. Carbon poured into the atmosphere from an uncertain source. Volcanic activity, methane hydrate release, or some combination of both. The oceans acidified. Deep-sea ecosystems collapsed. On land, plants and animals shifted their ranges toward the poles. Many species that couldn't move fast enough or adapt quickly enough disappeared. The ones that survived often did so by being small, mobile, or generalist enough to tolerate changed conditions. It took roughly 200,000 years for the planet to return to something like its previous state. The PATM is the closest geological analogy scientists have to current carbon-driven warming, which is why it appears so frequently in the climate literature. The difference that keeps researchers awake is the speed. The PATM unfolded over thousands of years at minimum. The current rate of atmospheric carbon increase is happening orders of magnitude faster. Then there is the Younger Dryas, which is a different kind of extreme. Around 12,900 years ago, as the last ice age was ending and temperatures were already rising, something abruptly reversed the warming. Within decades, not centuries, not millennia, but decades, the North Atlantic region plunged back into near glacial conditions. Average temperatures in parts of Europe dropped by as much as 10 degrees Celsius in less than a human lifetime. The leading hypothesis is that a massive pulse of fresh water from melting ice sheets disrupted the Atlantic circulation, shutting down the heat transport that kept northern regions warm. Sound familiar? The Younger Dryas lasted roughly 1,200 years and then ended just as abruptly, with temperatures rising sharply again in a span of perhaps 50 years. Ecosystems that had adapted to warming conditions suddenly faced cold. Ecosystems adapted to cold suddenly faced warmth. Many didn't survive the whiplash. The pattern in all of these events is consistent. Earth recovers. The chemistry eventually rebalances. The magnetic field reorganizes. The atmosphere restabilizes. The ocean circulation finds a new equilibrium. The planet is extraordinarily resilient over the timescales it operates on. What is less resilient are the specific arrangements of life that evolve for a specific set of conditions. Species are not adapted to Earth in the abstract. They are adapted to the particular temperatures, the particular chemistry, the particular seasonality of the moment their lineage evolved in. When those conditions shift faster than evolutionary adaptation can follow, the result is not adjustment. It is replacement or extinction. That is the honest framing that deep time provides. It is not a source of panic. It is not a source of comfort either. Not exactly. It is a clarification of what is actually at stake when scientists measure a shortening day, or a weakening magnetic shield, or a current slowing in the Atlantic. The planet has survived everything it has ever encountered, which is cold comfort for the specific ecosystems and the specific species, including this one, that evolved for the conditions that currently exist. Step back from the individual phenomena and look at what the full picture shows. The inner core is spinning differently than it was. The magnetic field is weakening in ways that exceed the models. The poles are drifting faster than any previous generation measured. The oceans broke their own temperature records and kept going. The days are getting shorter in increments too small to feel, but large enough to break atomic clocks. None of these are predictions. None of them are projections from a simulation. They are measurements. They are happening now, and they are happening at the same time. There is something specific about that simultaneity that deserves attention. Earth science has always had open questions. Every era of research has its unsolved problems, its anomalies, its data points that don't fit cleanly into the prevailing models. That is how science works. But the current list of open questions is not a normal list. It is not the ordinary scatter of unresolved edge cases. The inner core reversal, the South Atlantic Anomaly's acceleration, the polar drift exceeding projections, the ocean temperature spike that climate models did not anticipate. These are not peripheral puzzles. They sit at the center of how the planet functions. Several of the largest coupled systems on Earth are behaving outside the boundaries that the best available science had drawn for them. The crucial difficulty lies in their interconnection. These systems are not independent of one another. The magnetic field protects against cosmic radiation that shapes atmospheric chemistry. Pole position influences ocean circulation patterns. Core rotation affects day length and atmospheric dynamics. When several foundational systems shift simultaneously, their interactions compound in ways that remain unpredictable. Civilization was built on a set of assumptions so stable they were never written down. The poles stay roughly where they are. The magnetic field holds. The seasons arrive in the order they always have. The oceans warm or cool within ranges that agriculture and infrastructure can absorb. These were not naive beliefs. They were well supported by centuries of observation. What is changing now is not that the assumptions were always wrong. It is that the conditions that made them reliable are shifting, and the shift is fast enough to observe within a single research career, sometimes within a single decade. What makes this moment genuinely different from any previous moment in Earth science is not the changes themselves. The planet has done stranger things. It has reversed its magnetic field completely, dropped into ice ages, warmed so fast that the oceans turned acidic within geological eye blinks. The difference is the instruments. No previous civilization could watch the inner core with seismic arrays sensitive enough to detect its rotation. No previous civilization had a network of satellites mapping the magnetic field continuously from orbit, measuring the South Atlantic Anomaly in real time as it deepens. We have built, in roughly the last half-century, a set of tools that can read the planet's behavior at a resolution that was not previously possible. And what those tools are returning is a picture more complicated than the one they were built to confirm. That is both the most important thing about this moment and the most difficult thing about it. The knowledge exists. The measurements are real. The open questions are precisely stated. Scientists know what they don't know with more specificity than ever before, which is exactly what science is supposed to produce. What comes after the measurement? How institutions respond, how societies weigh long-term signals against short-term pressures, how civilization recalibrates assumptions that were built into infrastructure and policy and agriculture long before any of this was visible. That is a different kind of problem. It does not have a scientific answer. It has a human one. The planet is telling us things it has never had a listener attentive enough to hear. And for the first time in the history of the species, we have the instruments to listen. What we do with what we're hearing is the question that doesn't have an answer yet.